Hello everyone, this again is the DBE November 2019 paper, the physics paper 1, and we are now on question 7. Question 7 is an electrostatics question, and from what I can see with my notes is that you did a lot of this in grade 11. Okay. If that's not the case, then you did in grade 12. Sorry. Okay. So the question 7 goes as follows. A small sphere, Y, carrying an unknown charge, is suspended at the end of a light, inextendable string, which is attached to a fixed point. Another sphere, sphere X, which is carrying a charge of plus 6 times 10 to the negative 6 coulombs on an insulated strand, is brought close to sphere Y. Sphere Y experiences an electrostatic force and comes to rest 0.2 meters away from sphere X, with a string at an angle of 10 degrees with the vertical, as shown in the diagram below. Okay, so what happens is that, okay, so we have sphere Y and we have sphere X. Uh, they were brought close together and then they obviously like exchanged forces whenever there's a whole interaction, and then sphere Y went out to 10 degrees and 0.2 meters away from sphere X. Okay, there's a 10 degrees there. Okay, now we are asked in question 7.1.1, what is the nature of the charge on sphere Y? Choose from positive or negative. Okay, now we must remember that in electrostatic forces, forces with the same sign repel and forces with different signs attract. Okay, so the same signs repel each other. So, for example, if there was a positive and a positive, they repel each other, or a negative and a negative repel each other. It's basically like if you took two magnets and you put two of the same sides together and they repel, and you put the different sides together, then they attract. It's like a magnet. Okay? And the opposite sides, opposite signs attract. So if you put a plus and a minus together, then they will attract each other and they will pull each other closer towards each other. When they're repelled means that they're pushing each other away from each other. Okay. So what is happening here between X and Y? It seems to me that they are repelling each other. Why? Because they are 0.2 meters apart and they are staying apart. If they were together, that means that they would be attracted to one another and they would stay attracted to one another. Because this sphere Y is only being kept 0.2 meters apart from X by literally just by the force from X. This string is only keeping it up. It's only keeping this is only keeping ball Y from falling to the ground. Only keeping it up. X must be pushing it. X must be pushing Y that way for Y to stay there. So X has to be pushing Y to the left, because otherwise Y would be touching X. Gravity would pull Y towards X if it wasn't charged. So, and if they were attracting each other, they would be pulled together. Okay, so they're repelling, and we said the same signs repel each other. X is positive, which means Y also has to be positive. So our answer for this question, 7.1.1, is that sphere Y, sphere y is positive. Okay. And if you had to give a reason for it, you would say that sphere y is positive because sphere x is positive and they are repelling each other. The same signs repel each other and um, opposite signs attract one another. Okay. So moving on to the next question, we are told to calculate the magnitude of the charge on sphere y, which is the yellow-orange one, sphere y, if the magnitude of the electrostatic force acting on it is 0.3 is 3.05 newtons. Sorry. Okay. So what is this force? Okay, so the force acting on, if we had to draw a free body diagram for sphere Y. Okay, no, actually, that's in the next question. So let's just draw on here. So the electrostatic force pulling Y to the left from X is 3,05 newtons. And we're asked to give the charge on sphere Y if it's 3,05 newtons, putting it that way. Okay, and this is the magnitude of electrostatic force. So we're looking for magnitude of the electrostatic force on, oh, so we're given the electrostatic force is 3.05. We're looking for the magnitude of the charge on sphere Y. So if we look at our formula sheet, the charge is Q, electrostatic force is F. Okay, and we already have the charge on X, we're going to use that as well. That is the other Q. Okay, so if we look at our formula sheet, the formula for electrostatic force is as follows. F equals K, which is a constant, Q times Q1, which is the charge of the one sphere, times Q2, which is the charge of other sphere, over the radius squared. The radius is the distance between the spheres. Spheres, and that's always in meters. Okay, so now we can put all of this in. We are looking for the charge on sphere Y. So we can say that Q1 is X and Q2 we can say is Y. You can put 1 and 2, you don't have to put X and Y, but it's going to make it easier to explain. Okay, so we're told that the electrostatic force experienced by acting on it is 3.05 newtons. Okay, so that means that the electrostatic force between the two, this force putting them apart from each other, is 3.05. So we can put that in there. 3.05 equals, so K is 9 times 10 to the 9. That is on your formula sheet. You will get that. The charge on sphere X we were given is 6 times 10 to the negative 6 coulombs. Times 10 to the negative 6. And we are looking for the charge on sphere Y. Over the radius, the distance between the spheres, we were told over here is 0.2 meters. Over 0.2 squared. Okay, so now how we work it out is we go 3.05 times 0.2 squared equals, and we can times these out of here on our calculator. 9 times 10 to the 9 times 6 times 10 to the negative 6 is 5,000, 54,000 times QY. And if we go 3.05 times 0.2 squared, then we get 0.122. Therefore, QY, so what we do now is we go 0.122 divided by 54,000. So QY equals 2.259. We're going to round to 2 decimal places. So that becomes 2.26 times 10 to the negative 6 coulombs. Because we're looking for charge, and charge is measured in coulombs. So our unit is coulombs. Please make sure that you use the correct units for all of your sums. Okay. Next question. We are asked to draw a labeled free body diagram for sphere Y. Okay, let's remove all of this stuff and see what's happening with sphere Y. Okay, so sphere Y is being held up off the ground by a string. So we can say that it's been held up by tension, right? It's being pulled up. It's overcoming gravity by the tension. Okay. It's overcoming gravity by the tension. So we mustn't forget we've got gravity pulling it down. Force of gravity pulling it down. You would remember in question 1 or 2, I told you that we have a normal force which acts against gravity, but we must remember that there is no normal force here, because normal force only happens when your object is sitting on a table or is on the floor, and the object that it is sitting on produces that force that acts against gravity. So there is no normal force in this one. And then we also know that we have the force from X, which was the electrostatic force that is pulling sphere Y towards the left, away from sphere X. And that was the electrostatic force, which we can say force electrostatic. Okay, so those are all of the forces acting on sphere Y. So now that we've got that sorted out, now we can go and draw our free body diagram, which you just do a dot and then you extend all the other things out. So let's do it here on the side. This is 7.1.3. And we have our dots, and we're going to draw our nice straight lines up, and this one, oh my word, that is tension from the rope. We have the force of gravity pulling us down, and then we have the electrostatic force pulling us to the left, away from X. Okay, that is our free body diagram. Now they have asked us to calculate the magnitude of the tension in the string. So what we want to know, how much is this tension? Okay. How much is this tension in the string over here? Okay. So I hope that you guys can see that we are going to have to use some nice maths in this question. We're going to have to do some trigonometry because you've got angles. This tension is coming up from an angle, and we need to work out what the tension of the string is, and just going to be the whole thing. Okay. So, tension over here. That was also the hypotenuse. This is the opposite angle, and that is the adjacent angle. That's 90 degrees. Now we would say, okay, that the sine of 10 is and then this is the electrostatic force. The adjacent angle is the electrostatic force. We'll also just put that in our picture. Say the sine of 10. So sine is opposite. Sine is opposite over adjacent. Okay, this is the opposite side, sorry. Oh, never mind. Hang on. That's not the adjacent side. This is the opposite side. That is the adjacent side. So sine is opposite over adjacent. So sine is F for electrostatic force over tension. Therefore, the tension is the electrostatic force. No, sorry. The tension is the electrostatic force over the sine of 10. Okay, so that's what the tension is. Working this out, but we can just go straight back from this. Okay. Now we want to know, okay, so we want to find out what the magnitude of the tension in the string is. So we're going to start from the top. The net force in this system, because it is not moving anyway, everything is stationary, the net force is 0. Okay. So I said that tension was Fe. Back here, from all this working out, you can write this nicely in your actual answer. So let's go back actually. We can say the sine of 10, from our little drawing is equal to Fe over the tension. Therefore, the tension equals Fe over sine 10. Okay, so there's two ways you can do it. You can either say tension equals Fe over sine 10, or you can say Fe equals tension sine 10 degrees. Going to get the same answer for both. Then we can sub in here, and we worked out in the last question that, we were given that the electrostatic force is 3.05. So we can put that in here. 3.05 over sine 10. It's tension. And 3.05 is T sine 10 degrees. And for both of them, we get that's tension is 17.56. And tension is always measured in newtons. So our thing on the end there is newtons. Okay, so let me re-explain this quickly. Tension, we have the electrostatic force, and then we just have the string. This we were given is 10 degrees. This is 90 degrees. Therefore, because of our little triangle rules, we know that this angle over here is 80 degrees. So what we can also do to find the tension is we can also use cos, the cos of this side. And we say because is cos is adjacent over hypotenuse. Okay, it is adjacent over hypotenuse. So cos 80 degrees is adjacent over the hypotenuse. Therefore, the tension is Fe over cos 80. Okay, know that the Fe is 3.05, and therefore the tension, we should get the same answer. Oh no, okay, hang on. Okay, so you can also use cos, and then you should get exactly the same answer of 17.56 newtons. Okay, and remember it's newtons because you're measuring because we are measuring tension. Right, so we've done the free body diagram, we've done, oh sorry, I labeled this wrong, the magnitude of tension and the string. Okay, now we are moving on to section 7.2. And now this is a whole different scenario. We are told that we've got two small charged spheres, A and B, A and B, okay, on insulated stands with charges 2 times 10 to the negative 5 coulombs for A, as shown on the diagram, and negative 4 times 10 to the 5 coulombs. I'm saying to the negative 5, sorry, coulombs, respectively. So for B. They are placed 0.4 meters apart, as shown in the diagram below, and M is the midpoint between spheres A and B. Okay, so without even looking at the questions, we can see we've got A is positively charged and B is negatively charged. So from just seeing that they have different charges, we can tell that what? Okay, so the same signs repel, opposite signs attract. So what is happening to these charges, to these charged spheres? They are attracting because opposite signs attract. Okay, so the spheres are attracting. So that means that both of their forces are working towards the middle because they want to get together. They want to touch, they want to get together. Okay, because they're attracting each other. Okay, now our first actual question for 7.2, 7.2.1, they've asked us to define the term electric field at a point. Okay, the definition for electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. Okay. Lovely. Now it's easy, 2 marks. Fantastic. Okay. 7.2.2 asks us to calculate the net electric field at point M. So here at point M in the middle, we are experiencing some force coming from A, and we are experiencing force coming from B, and the force experienced at point M is the sum of the force from point A and the force from point B. Okay, we're going to add them together, and yeah, we're going to see how much that is. Now, we must remember that because M is in the middle and the spheres are 0.4 meters apart, M is 0.2 meters from A and 0.2 meters from B. So when we do our calculations, we must make sure that we have the correct radius. We cannot use 0.4 meters because that is not how far point M is from A or from B. A and B are 0.4 meters away from each other, not M to A and M to B. Okay. So now how are we going to calculate this? So first we need to calculate what the force is, what force M is experiencing because of sphere A, and what force M is experiencing because of sphere B. Okay, so we're going to start with sphere A. So we're going to write here electric field, because they asked us for the net electric field. Sorry, not the net force, net electric field, but same thing. Okay. Because we said electric field was electrostatic force experience, so it is a force. Electric field at M due to A. We're going to explain it all nicely out for the examiners. Okay. So our formula is the electric field, the electric field because of A is K, which is our constant, times Q, which is the charge of A, up QA then obviously, over the radius squared. Okay, remember the radius is not 0, 0.4, it's 0, 0.2 because M is halfway between. Okay, we can write everything in here nicely. Radius is 0, 0.2 squared. Okay, and that means that the electric field at M due to A is 4.5 times 10 to the 6 newtons per coulomb, -1. Okay. And the sphere A is positively charged, right? And sphere B is negatively charged. So sphere A was positively charged. We'll just make a note of that, but we are not going to put the charge in there. We're not putting the charge. It doesn't matter if it's positive or negative. We just want what the force is. Positive and negatives are only going to tell us which way it's pulling. Okay. Now we need to find out what the electric field at M due to B is. Okay, and B, that is sphere B, obviously. Okay, we're going to do the same thing, but with the charge of B, not the charge of A. Remember, B is negatively charged, but we're not putting the charge into this one. Okay. When we are doing the big sum with both of the charges, if the one is negative, then we can put the charge in there. Um, and then that will tell us what direction is, but we don't put it in this one. We just use it at the end. Okay. And then we sum everything in. Charge of B is 4 times 10 negative 5, no sign, over the radius is 0.2. Then we get the charge due to B is 9 times 10 to the 6 newtons per coulomb minus 1. Therefore, the net electric field at M is the electric field due to A plus the electric field due to B. And that is the electric field due to A was 4.5, 4.5, 10 to the 6 plus 9 times 10 to the 6 is 1.35 times 10 to the 7 newtons per coulomb minus 1. Okay, we weren't asked to give a direction, so we can just leave it like that. Okay, so that was this question. Just remember, when it's the small equation, you don't put the signs in when you're working out either one. Okay, you will just get the overall what direction it's going using the signs. Okay, so this was question 7. This was electrostatics, and I hope that the section goes well in your exam. Thank you.